During that magnitude 8.8 earthquake, less than 1% of modern engineered structures were seriously damaged. In contrast, in Haiti, the same year, just a few months before the Chile earthquake, in Haiti, where there are essentially no building codes, most buildings were seriously damaged or collapsed, and about 300,000 people were killed. So there was a huge contrast there between Haiti and Chile, and it's attributed directly to building code. Canada is certainly one of the world leaders in building codes with the United States and Japan and Chile. They really provide the engineers with the information they need to design a structure so that it doesn't collapse during an earthquake.
So we do have significant seismic risk in the west, and we have medium to high risk in the east. But the central part of the country is pretty stable. Where we do large-scale testing of structural components, we test structural and non-structural columns, frames, walls, mostly reinforced concrete, but we will be testing some timber components as well as steel components under reverse cyclic loading to simulate earthquake effects. Well, in this area, we are building a number of specimens again for seismic testing. Here you see foundation of a masonry wall, and we will be using concrete block walls and then retrofit them by using fiber reinforced polymer material, FRP material, to strengthen them against earthquakes. And at the back you see building columns that are being built. You can see inside the transverse reinforcement is widely spaced. Normally we require 3 to 4 times as much steel, so this is seismically deficient, and hence it will be retrofitted as well. At the back you see some shear walls under the supervision of Dr. Palermo, and he is doing some research on performance of reinforced concrete shear walls. I would like to show you some fiber reinforced polymer material. These fibers have 10 times the strength of steel, and it looks like wallpaper, and it's very easy to handle. It's very light. You can cover entire wall or a structural element with this, and then it does strengthen structural elements. And we also use FRP bars as opposed to steel bars, and putting concrete and reinforcement inside FRP cage like that, a tube like this, which we refer to it as stay-in-place formwork, also improves ductility, the formability of concrete columns, and this is a new and promising material that we use for seismic applications.
When we design structures for earthquake, it's different from wind, or from snow, or from the load of the occupants, right? Major earthquake doesn't happen so often. It only happens once every several hundred years, even thousands of years. But when it happens, it causes such a devastating effect, right? So it is considered not economical to design structures to remain undamaged after major earthquake, because that would make everything so much more expensive. It's a balance of safety and economic costs, right? But as long as during and immediate after the earthquake, the structure would not collapse so that the occupants can safely get out of the structures.
My presentation at Carleton next week will be earthquakes in general, what causes earthquakes, why do they occur, where do they occur, and then really focusing on how earthquake science can help protect us from future earthquakes.